The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
For today, there are 3 more lectures, and we make it 2 guest lectures. One will be on the reliability of the materials at high temperature. This is original and the last lecture. Also have to juggle around the schedule everybody. So instead of what I would do is the next Friday, we'll be talking about the reliability of the materials. This is Professor Christopher Shu in the materials department. He's been doing research in this area for a long time. Hopefully we'll be better taught than I could get. And then on the week after next week, we will have Dr. Ivan Sananovich talk about selective surface. He's been working on solar thermal photovoltaics. And so he has done a lot of work in the spectral control area. So he'll be, again, better talk than me. And then, say, the final lecture, we will be come back a little bit to talk about how we combine selective surface with thermoelectrics and with also photovoltaics. Okay, so we have learned thermoelectrics, we have learned photovoltaics also. So that's solar solid-state solar thermal energy conversion. And today, what I want to cover is the mechanical energy conversion, solar to electric solar thermal, but via mechanical means. So let's recall what I was talking in the previous lecture. We talked about black body radiation. We mentioned a little bit on the Earth's motion and how we usually test solar spectrum, AM0, AM1, AM1.5, etc. And then we define radiative property, those definitions, many different definitions, as I said. I don't expect that you'll remember all those details. The point is, for spectral control, it's very important to understand the wavelength dependence of the properties. And then with that, we discussed the maximum efficiency of solar thermal engines and maximum achievable temperature. And again, we emphasize the selective surface. But you don't know how to do it yet, but it's important. So in today's lecture, as I said, I want to cover really the solar thermal mechanical part. And what we'll start with is the hot water system, solar hot water. And then we'll talk about to bring up to a higher temperature, we'll talk about the solar concentration. And we'll talk about the maximum, how much you can concentrate the solar radiation. And then we look at how you could, in practical, to do different ways of concentration. And to do concentration, you'll need to track the sun. That's one of the challenge. So I'll talk a little bit about tracking and non-tracking. And then go to solar mechanical. If I have enough time, I'll start a little bit, give you a preview of what control the surface properties in the electromagnetic wave. So, solar hot water, right? It's very mundane, but I really appreciate this. As probably mentioned before, when I was a kid, I grew up in China and didn't have a chance to take a hot shower. And now when I go back to my parents, they still live in China and they use solar hot water. concept, of course, is very simple. Solar collector, you absorb the solar radiation, and you heat up the water. Very simple concept, right? And also, I want to give you a very simple backup email. So if you're a mechanical engineer, this will be pretty easy, but I did this for the preparation of the class, also out of my own curiosity. First year from materials, this is probably a little bit more, say, not very familiar with you, but it's a simple energy balance. So what I want to ask is how much, if I want to put in my own house, what's the area I live, right? Solar hot water. And typical household water tank is about 80 gallon. It's a larger house. If you have smaller, so ranging from 40 to 100 gallon range, I guess. And if I take a start temperature of water at 15 degrees, and I want to keep the water tank at 60 degrees Celsius, so during the day, right, let's suppose I deplete all the hot water during the night, and I want to store 80, during the day I want to heat up the water from 15 degrees to 60 degrees. And so you want to say how much, what's this solar surface area, hot water surface area you want. And it's simple energy balance, right? During the day, how much solar radiation received, and then of course you consider efficiency of the absorber, and then that balance to heat up this much water, how much energy you need. So you do that energy balance, the area that what I want, the solar radiation, insolation, and time of the day, efficiency, and of course the heat capacity that's stored in the hot water. So you put in those numbers. Typically, when people calculate, you can see it's a little bit optimistic. If you live in Boston, you don't get 1,000 watt. Okay, and I took a standard calculation, 1,000 watt, 5.5 hour. So that's an average. The whole day average. Typically, that's what the people take when they test the solar cell. 1,000 watt, when they calculate solar cell output. And efficiency of a solar thermal hot water system ranging from, I'll tell you how to estimate efficiency, but I take a typical number, 60%. Okay? So I need 5 meters here. Okay. And in China, I know it's very cheap. And typically people install somewhere 1.5, 2 meters, so it's a lot of very big tank. Most people live in an apartment and they use less water. Okay, in terms of solar hot water, there are different format. One of the format is a flat panel, right? So here we have, what we have is an absorber. That's typically is frequency selective, meaning they absorb solar radiation, but do not, or you want to re-emit a very small amount of thermal emission when it heats up. And so you can say the backside is the insulation, and this is absorber tube, could be on top or on the bottom. And typically they do not, so in between is air. Okay? And the tank could be on the top of the absorber itself. So in that case, you don't put a tank in the basement, and you can use the gravity of the water to drive the water flow, to drive the hot water down. But say the problem is your water flow rate is a lot, depends on how high you put the tank. So if you live in low buildings, your pressure is low. This is the example. Clearly, water tank is not on the roof; it's in the basement. And in that case, you use a pump to pump the water, so it's a pressurized system. So they're pressurized, and this one is not a forced system, just natural. And the one that's what I thought really interesting is this vacuum system. And this is predominantly used in China, and it's a glass, so it's a double layer glass. Inside is a black coat. What looks black is actually inside. Well, outside is another glass, clear glass. So it's a circular, and the inside glass is first coated with selective surface, and then you evacuate it. You seal on the other side. So it's a double jacket, and on this side, because of vacuum, so it has a getter. The getter, what does getter do is say the evaporation is actually collected by this metal, react with whatever evaporates, and so you would imagine, so putting vacuum under sun, how long it lasts. And I actually visited some of this, the father, the father of this technology in China. And he said that he put this stuff early in the 90s in Tsinghua. He's from Tsinghua University, and still working, so up 20 years. And that's consumable because if you think about, in my house, I bought a TV. I remember my first TV is still working, about more than 20 years. And that's a CRT. It's a vacuum technology. Right? Say the screen of the TV, say the cathode ray tube inside is actually ultra high vacuum. So the vacuum is pretty high, and you can do a calculation and find why if the vacuum is too low, the air conduction makes too much heat. So this is evacuated tube. That's glass. This glass is really cheap. I visited the manufacturing site, and the whole tube is about this high. The diameter is 50 millimeter, and the manufacturer of the double glass tube is about $1.5 per tube. So really cheap. This one is a little more expensive. It's not a glass, and what it has is a metal absorber. So it's it could be a copper or aluminum. Again, this is a cost, right? This is really the cost is crucial here. And this is selective absorptive coatings again. And so what it does is this is a heat pipe. So the heat absorbed conducts to the heat pipe. So heat pipe diameter is not this big. That's too much copper, right? It's a small diameter heat pipe. And so the heat is evaporate the liquid inside the heat pipe. And on this side, you have forced water heat exchanger. Forced water take the heat away. So this is one of the cheap forms unpressurized. So what it has is the double glass layer. You fill the glass inside glass with water. I go back here, inside, right? This is empty. So you fill with water, and when it heats up, natural combustion. So the hot water goes up here, and the cold water flows down. So there's it's a passive system, no pump at all. And you put on the roof, and then you can take a shower. So that's a typical family in China probably is about 15 to 20 tubes. And this one is a forced pressure, right? You put a separate tank, you put a pump through, and forced cooling at the end. Okay. So that's what the system looks like. Again, out of my own curiosity, I say, okay, I'm going to estimate what's the efficiency of the system, flat panel and vacuum systems. So this is a vacuum, a model for a vacuum system, where I have a cylinder. Inside is a cylinder, inner cylinder. So this cylinder, there is one. So actually, this is a self-tracking, right? No matter what sun direction is, there is always side wall is facing the perpendicular to the sun. So this does have some advantage there. In fact, there's a startup company called Cylindra. and they are putting solar cells like this. So circle along the circle of the cylinder. And it's vacuum in between, so incoming solar radiation is just the cross-section area. That's I count the outer diameter, and say the insulation, solar insulation. So absorbed, how much is absorbed? In terms of absorption, the first thing you have to go through is the outer glass layer. So that's a transmissivity top. And then inside the surface is absorbed. Alpha is the absorptivity. So that's absorptivity to solar radiation. Now this is a disadvantage here. The radiation loss. Right? Radiation loss because the whole inner tube is heated up. So the surface area is actually pi times the inner diameter. It's not just the cross-section flat. Compared to flat, it's only the flat area. Now it's the whole surface area. And then that's the emissivity. And I do a black body, simple black body calculation. The surface. So what I did not consider is a multiple reflection. The surface emission, I just say, okay, everything goes to the environment. And in reality, some of those cannot go. In fact, the glass may trap some of the radiation back, reflection, and also the glass is non-transparent in certain wavelength range. So with that, I can say this is the absorbed radiation minus the loss. That difference is what I actually get into the hot tank, and then divided by what comes in. So I have my efficiency. So this is a simple, again, back of envelope, okay, for fun. Yes?
Question. So the tube is pretty large. I think what half the total surface has the solar radiation?
That's not.
Do they have the path reflector?
That's one half, right?
Oh,
it's cross-section area, but the emission is pi d. So that's a disadvantage. Okay. And so that's an idea. I'll show you the curve later on. Now let me go look at the hot water flat panel type. So flat panel type in between is the air. I was actually curious whether people use double glaze windows here or not. And what I found is it seems that they do not use it. So it's just one layer of glass. So this is the air and selective surface. And of course, when you think about heat transfer, this absorbs solar radiation and then will conduct through the air, conduct through glass, and outside is electrical convection. So you have the resistance in series. Conduction, air conduction resistance, glass resistance, convection resistance. So that's one part of the heat through conduction and convection. And backside, the thermal insulation can still leak heat. So backside I have a conduction. And then I have radiation goes through directly. So I have three paths for the heat transfer. And this is my simple circuit. The solar radiation comes to the selective surface. The energy now, one part is go directly through radiation, and the other part goes through the air, glass, convection outside, and then the backside, the insulation. Okay. And I put a resistance because this is something. If you're not the mechanical engineer, didn't take heat transfer before, this is probably less familiar. But this is similar like a circuit. Okay, thermal resistance. You do the resistance calculation for air, the thickness divided by thermal conductivity, so the gap thickness divided by conductivity divided by area. And they say if you do that, why don't you use thicker? And the problem is once you use too thick, there start a circulation, convection start to happen. So you look at the double pane window in the typical window, that thickness is not it's a few millimeter thickness. So you don't use too thick here. So here I took a 10 millimeter. And then say glass. Glass is a few weeks ago, there was a talk, somebody is going to install a flat panel system in one of the MIT building, MIT, I don't know. Ashton? Okay. I was surprised, the cost curve was just a surprise to me, because that's like a 13, 15-year return. I don't understand why, but say, it looks like they use very tough glass. This is a steel. What's the glass like? You harden the glass. You can walk on it. Okay, so, but anyway, but glass resistance is very small. It's really air resistance, convection resistance. Those are the resistance that cause the total. That's this side the resistance, and then the insulation resistance on the back side. So I put all this number together and did the energy loss. Again, consider all the radiation. So I have radiation loss. I have the conduction loss. The conduction convection loss. And with this loss, I can again go calculate how much energy comes in, absorb, minus loss divided by what comes in, and that's what I have. Okay. Those numbers, I assume, for example, in the next graph, I assume 95% absorption, 5% emission. This is what the industry can do. So we have a researching a group on selective surface. Always I say, how we can do better. Industry can do that at the meters per second. Okay, selective surface. 95% absorption, 5% emission. And this hot water is, of course, the typical operational temperature is about 70, 80 degrees. So they do not operate at very high temperatures. And then when you go to higher temperature, if you can go 500 degrees still keep this, you will be the best in the world. It's very hard to do that. Okay, that's the curved icon. That's the vacuum system. And this is the flat panel system. And efficiency depends, of course, the temperature of the water. Essentially, the temperature of the selective surface there. And I went to a web and I found this. Depends on who you are, which website they're looking. People have different curves. But I found the one that I thought closer to what I have. So this is one company that said that's a vacuum system that compared to flat panel. A flat panel goes to almost zero. I don't believe that. That's probably too small. Okay. So, but solar thermal is efficiency compared, of course, to the photovoltaic is many times better. And so in terms of, if you look at what has been used, is this is a chart I got from this publication. Here is this side is solar thermal. That's it's compare all the renewables. Solar thermal. Here is wind. Here is geothermal, photovoltaics, solar thermal power plant, ocean tidal power. And you find out that total capacity and the red is actually produced energy. So you can see the solar thermal is actually a pretty large part of how people are currently using renewable energy. Okay, just heating up the hot water mainly. And this is in terms of technology. Flat vacuum tube is dominant because China use it. And flat panel 32%, unglazed collector and air collector. So this is where it's being used. You can see the China is off the chart here. It has about 100 million square meter installed. I don't understand why we don't use it here. And, but I did say, I think Hawaii now has legislation you have a new house being built, you have to put in hot water system. Tim, you're from Hawaii, right? You can go back check. I was once talking to, and every time I have a chance, I always ask the people why. And also, price gets very high. That's probably because in China, you can typical household is $300 to put a solar thermal system on the rooftop. Okay, so that's solar thermal. Now we want to go to higher temperature, right? Solar thermal is 80 degree, 100 degree, and we want now go to higher temperature. And to get to higher temperature, you need a concentration. And now we need to look at the concentration. Let me remind you, I showed this before. The Earth itself, say the orbital is not just perpendicular to this plane. There's a 23.5 tilt of the Earth, right? So on this side, this is tilt. On this side, the same tilt. That tilt is fixed. That's why we have summer and the wrong tilt direction. We have summer and winter. Okay? And the degree sustained of the sun by, say, if you view from Earth, the degree is 32 seconds. So that's about 0.5 point. About 0.4, 0.5 degree. Okay. And now the question I want to ask first is, if you do concentration, how much you can get? What's the maximum concentration, right? So we can look at the theoretically, what's the limit? The maximum theoretical limit is I cannot heat up an object hotter than the sun, right? And now, so that you all agree. But if I ask you, can I concentrate radiation even with intensity hotter than the sun? Not hotter, the intensity higher than the sun. Is that crazy or not? Huh? Okay, you'll see it later. Okay, so first let's look at we'll just look at energy balance. If I think about the spherical radius from the sun, right, and the area of the sphere times the energy flux, and area of the is a constant. Once the energy leaves the surface, the larger you draw circle, the less is your intensity. So the intensity of this Earth, you think of a circle here, that is a capital R, 4 pi r squared times whatever insolation outside the Earth's atmosphere. Right? So this is the insolation outside the Earth atmosphere. This is the intensity on the surface of the sun, radius of the sun. So that's the energy balance. Conserved, always. Of course, you say, oh, there's something in between, scatter a little bit light, consuming the space is pretty much all empty. Right? So now let me concentrate. If I concentrate this concentration ratio and this intensity on the Earth surface, or the Earth of the Earth's insolation, and this is the energy I put in onto an object that received this concentrated light, right? So energy balance will tell me, in this case, again, the object should be black body, actually, because you want to absorb every drop of solar radiation. And because you absorb the solar radiation, you also re-radiate. So you want to absorb maximum, you also re-radiate maximum. So it's a black body. So actually, I put a say the energy absorbed, the balance, the energy radiated. I do perfect insulation. So this is per unit area based. This is per unit area based. So that's the energy balance for the object that received the concentrated light. And of course, as I said, my condition is that this object cannot be hotter than the sun. Right? So this is the concentration, and from here, I get my maximum concentration happens when this is equal, and that's the solar flux intensity divided by whatever incident in the Earth. So that's R over small r based on my energy balance. And if you look at R small r, and this theta here is a half angle sustained to Earth. So that's a sine theta squared. So that's my maximum concentration. And if you plug in the number, I said the 2 theta is 32 seconds. So you plug in number, that's about 4,600 times, 1,000 times. It's the maximum you can get. It's not the maximum. People actually have achieved higher than this one. Okay? This is because the emission inside the object is proportional. I have one mistake here. It should be proportional to n squared, not proportional to n. Okay? So the emission inside object is proportional to n squared. So if I have a medium, like water or glass, right? The intensity inside could be higher than the vacuum. Black body intensity, n squared. N in glass is 1.5, so square is 2.25. And if you use silicon, the n is about 3.5, the square is about 10. Right? So if you do that, again, your limit is the temperature limit, is not the intensity limit. Your temperature of the concentrated surface cannot be higher than the temperature of the sun. You do that, you get your maximum is n squared sine theta squared. Okay, so that's higher than the previous one. And indeed, this was achieved in the lab. This is Roland Winston. They have, I'll talk about this in more detail. This is a compound with the focus and non-focus, and they have achieved 56,000 in the lab. Okay? So that's the, from the second law perspective, your absolute upper limit. And now let's see how we can get there. Okay? And you think I'm going to use a lens. And this lens, if I think about the lens, okay, so all parabolic trough, right? We know that you have power light comes in, you focus one point. So that's the question is, what's the concentration limit if you, those are the image formation, right? Using a lens, using a lens or using a parabolic trough, you have a focal point. That's a focal point. This is the image. So image forming optics. And remember the sun sustained angle. That's the K, right? Even though we say solar radiation is a parallel light, but when you want to do focusing, you want to that angle becomes important because previously you already said. So what I want to say, think about is if I have either lens or parabolic trough, say the opening here is D, and the focus here is a small d. One is a big D, the other is small d. And I want to find the ratio. Okay, let's look at it. So if I do 2D, this one is a flat, right? Flat panel. If you do a tube, you have a different result. But here I'm a flat panel, and this is half of it. And now I look at this is a vertical, say perpendicular line here. So r times sine theta here is 2 theta. So this is really, if you think about parallel line comes in this way, and that's my reflection here. And this one is my this line reflection. So that's the edge of the solar cone there. And so r times sine theta gives me this one, right? Perpendicular line. And d over 2, so that's here, times, this is phi, and here is phi, so here is also phi. So d over 2 times cosine phi is all giving me this segment. So I have an equation geometry here, geometric relation. And then I have this r and this r is about the same, so r times sine theta gives me d over 2, right? The opening there. And then I have, from here I can get my relation. How much focus can I get? Capital D over small d. I have sine 2 phi divided by 2 sine theta. So this is the maximum you will get. This is the concentration you get. And you will see the maximum happens is sine 2 phi equals 1. Right? So 45 degrees. So when phi equals 45 degrees here, I have the maximum. And that maximum is 2 sine theta, that's 107. My calculation. Maybe you can go back to check. And if you use 3D, axisymmetric, you square that, and that's 4 sine theta squared. The problem is, now you can say this is a factor of 4 smaller than the limit. Right? Thermodynamic is 1 over sine theta. Here, if you form an image, your limit is a factor of 4 smaller. And how you can reach that maximum limit? Okay. So image optics is a little bit too constrained. Ideally, you want everything goes to one point, right? And you want to form an image. So this is there's another slide that I just copied from Winston's book. And if you want to focus on the cylinder, that's 1 over pi smaller than the previous slide. Now, there's another way to do it. That's a long image method. This is Roland Winston's baby, and if you read, his rationale is starting from this 1 over 4. How you can get to the maximum thermodynamic limit. And here is one way. There is no simple mathematics in terms of the shape of the concentrator. But this is how he would explain it. So this is where the area you want to, this is a flat plate example. You want to focus on a flat plate B prime to D. Okay? And this is the angle of incidence, right? So that's the maximum angle. Let's suppose this is the maximum angle that you accept the radiation coming in. If you have another angle higher than this, it will not get in, it will be blocked. So this is the maximum angle, so you take a string here. At this point, you take a string, this is the opening limit A. So you keep this string length fixed, and you draw the curve down. So this one will slide. So the angle of incidence equals reflection. That's what is following. This surface gives the surface such that the angle of incidence equals angle of reflection. Of course, it's a specular surface that's being assumed. And at the limit, this one, when it's here, the reflection angle goes to D prime. Okay? So that's the image surface this is the image method he developed. And now we can check whether this one gets to maximum or not. So this is again simple geometry. I have AC, this section, plus AB prime. That's the string length, right? And the other limit, so this is the edge. You look at the edge only. A prime to B plus BB prime, right? So this is the string length. This is the string length. And the same string. So it's actually a very convenient, simple way to do the geometry. But the surface is harder to express analytically. And see the symmetry AB prime, A prime B from symmetry, they're equal. So you get rid of two variables in the above equation. And your AC is your AC is this one times sine theta. So A prime times sine theta. And your concentration then is 1 over sine theta. Remember before is sine 2 phi over 2 sine theta. Now you got rid of that factor of 2 in the two-dimensional geometry. And you go to 3D, you actually reach 1 over sine theta squared. So if you put your theta angle of acceptance, right? If you just say, I only accept the solar cone theta s, when that's your maximum. You have to accept all solar within that 32 R, right, second. So that's your maximum there. But this is a convenient because, say, if you think about you design, you don't need that high concentration, but you want a large angle acceptance. Particularly when you have also street light, right? If you think about, you don't always have parallel light, you also have the scatter light. And then typically people take an 80-20, depends on where you live. And so scatter light is approximate isotropic in all directions. So tracking, if you track only the solar part, right, maximum concentration, anything that beyond that angle, you can't capture it. So that's 80, the 20% is gone. And so with this, this is the other examples. And if you read the paper, it's interesting. This is when you concentrate to a cylinder using the same string rule. You can draw this, and in fact, those curves shows different acceptance angle theta and the concentration ratio, and also the height of the height versus aperture. So this height aperture, right? And if you look at it, if you want 3 times concentration, that's about 21 degree, and the height aperture is about 2 to 1. And also, what's important is you can never make a perfect surface reflector. So every time the light bounces once, you lost a fraction of the light, right? So this surface is never perfectly reflecting, 100% reflecting. So you want to minimize that number of bounces, because every time it bounces, it's absorbed a fraction of it. And let's say aluminum is you can get about 97% reflection, but that's 3%. If you have 10 bounces, 97, 10 to the power, you get a small number, right? So you want to minimize it. So this is the average number of bounces he calculated for those geometries. Okay, so this is the concentration, right? Now you concentrate it. Particularly when you go to higher concentration, you have to track it. Because the only certain angle is accepted, right? So you have to go track it. So let's think about how we would typically how you should do tracking, right? Again, think about the Earth has this 23.5 degree tilt, and in fact, I haven't figured out all this a little bit detail in the Earth's motion yet. That tilt of 23.5 is the average number, which it turns out the Earth is actually wobble a little bit. So that wobble happens between 22 to 24.5. Okay, and this will be important when you do the high concentration ratios, the acceptance angle. So if you think about it, so that's what I listed. Think in the summer, right? Northern hemisphere, and in the winter, I come from the winter southern hemisphere get their share of the sunlight, and now let's think about the why. Of course, it's easy to think why you need the tracking. So at low, let's say your radiation coming perpendicularly, and when you come at the angle, the amount of energy you get is times sine theta. So you don't get all the energy you could get if you make this plate perpendicular to the ray direction, right? But say this insulation not only just a sine theta change. It also, if you think about the path length through the atmosphere, right? Different angle of incidence, the path length going through the atmosphere changes. 1 over cosine theta, thickness divided cosine theta direction. So, your insulation also changes. And if you combine all this together, those are some of the places people measure per square meter how much energy comes in. And so this is at the northern latitude 45 degree. Anybody remember Boston latitude? I thought I was going to check, but I forgot. Okay. So we're close around this number. You can say this not very good insulation. So my calculation was too optimistic. I need about 7 or 8 square meters for my household. Okay, so which direction you should track, right? If you have a solar hot water or solar panel, should you orientate the south north, east west, right? So of course this is the east west. This is the rotation. The angle rotation is the east west direction. So of course, if you do only one X tracking, you want the maximum amount of energy received your solar cell area or your aperture. Then you want to do the axis in the south-north direction, and then your rotation is so that it's east-west direction, right? And then say in the other direction, you remember the Earth is the tilt, right? During the summer and the winter, that degree will go back here, right? So this angle will fix your solar cell here, this on the summer, and then when you go to the winter side, this side, right, your angle change. So so ideally you want to track both directions. Okay. There is one case people have done before that I think it's interesting, where you do not need tracking, or you do seasonal adjustment. And this is when you have a low concentration, and people use a wave shape. So these are the, you put a solar cell here. Those surfaces are reflecting surfaces is a wave group. Okay, and now if you orient those waves in the east-west direction, if you think about east-west direction, those groups in the east-west, so you will use this one means you can, the light here, you don't need to put the solar cell, so you can actually increase the flux here by a factor of 2. You use less, 2 times less of area. So the typically for this geometry, those group geometry, you can get as a concentration ratio is 2.5 to 3 times. So you can operate in that range, low concentration range. And if you do a little bit, what you need here is a seasonal change, because the acceptance angle in the south-north direction will change. So, but there are also people now developing this wolfram with checking there. People actually do tracking, local tracking. So there are even people doing south-north direction tracking. But in theory, so for those low concentration, it looks like you put it in southwest direction. You still don't capture that sine theta, right? The solar insolation, that still will change because your angle coming at the angle, your projected area, you're not tracking perpendicular there. But you use less. In this case, if you do this concentration, you use 2 or 3 times less solar cell. So you cut the cost. Okay. So this is what we talked about is the concentration and tracking. And in terms of PV, people do solar concentrated PV. There's effort. There are some companies, startup company. I'm not sure how successful they have been in deploying. This is particularly when you think about the high efficient solar cells, like gallium arsenide. The maximum here you can get to about 40%. Right? That's very expensive. So what you want is to use a high concentration ratio to reduce the cost per unit area, say, in solar incoming cost. And but say I'm not sure how successful they are commercially. And we know one of the problems is actually the heat transfer is a problem. And the other is say it's I think it's very important to keep the light uniform. So if the higher the concentration you have, if your tracking is not accurate, your light goes off your cell, then so you're screwed. So that's the tracking accuracy becomes very important. Now I'm going to shift next to the solar energy conversion system, and the solar mechanical energy conversion. And the most popular in use is the trough. So the absorber is a tube, and you concentrate the light, and so this concentration could be either by parabolic mirrors or the Fresnel arrays. In this Fresnel, so you can see the mirror is individually adjusted. So this is not a say parabolic, but the angle of each mirror is adjusted so that the light focuses to the pipe there. It's called the Fresnel, but I think the Fresnel is, my understanding Fresnel is typical, meaning you read optics, that's a diffraction side. But anyway, and this is a dish where you concentrate you track 2D. Here you could just do 1D daily tracking, or I'm not sure people do a seasonal adjustment or not. And here you need a 2D tracking, is a dish structure. or you do tower, you have say station the mirror reflecting to the tower. And trough is the most commonly used. We'll look at the more trough structure where you have a periodic mirror and you have the pipe inside in the focal plant. And this is a typical pipe, the solar collector pipe. Again, it's a vacuum. So the vacuum is a pretty high vacuum here, 10 to the minus 3 millibar, right? And you can imagine the challenge because the pipe itself is a steel pipe, and then outside is coated with selective absorber. So this is a typically you can see the absorptance is larger than 95, emittance is less than 14% at 400 degrees C, and the outer clear glass is also coated, so it's anti-reflection coated. So the transmission, typical glass transmission is about 93%. Now get to 96%. And if you look at this, what's important is how you make the cell here, right? High temperature cell is really, let's say you have a tube 100 meter long and thermal expansion and cell. Those are really critical technologies. So typical trough plant, you got collectors, you have the steam turbine, and then you also have, very often you have to have the gas fire, so you have to cogeneration. What do you do in the night? Or what happens if you have clouds coming? That's actually a big headache there, particularly for PV. Okay, solar thermal actually is slightly better because the thermal inertia, thermal heat capacity, dampen that. That's one of the advantages that solar thermal has. And you could also do some storage. I'm not sure here it has storage, but you could do storage. And the solar thermal plant here, the fluid itself, you can see is a closed loop. The fluid through the pipe is closed. Or steam generation, steam turbine, typically if it's water-based steam turbine, so this is the other loop, the steam loop here. And in fact, in the pipe, they use oil. And the oil is one problem. You can't go to too high temperature. You go to too high temperature, you decompose. And so the oil has a stability. This is a still area where people are doing research, stability problem, and how you can develop higher temperature oils. You can get to higher temperature, but your oil will not know it. Okay, and this is just a picture here. If you look at the installed, typical installed and typical size of the plant is around 100 megawatt. 100 megawatt is small in terms of if you compare with the coal-fired. Right? Coal-fired plant typically one steam turbine there is 1 gigawatt. Okay. And this is too small. You can read your handout, but so those are examples. And what I want to point out that here are the concentration here. It's typically those concentration is between 60 to 80 cent. That's the concentration ratio. And they look at the cost of the solar thermal. That's the one case where different generation, 30 megawatt. This is a US dollar megawatt hour. So if you do kilowatt hour, you divide it by 1,000, so that's about 19 cents per kilowatt hour. Coal fire is about 5 cents power plant. So here is the 16 cents, and there's some projecting. You scale up, and that will go down to 10 cents. The efficiency, again, I'm not expecting you to read it. I'm just let me just quote the few efficiency numbers. The collector efficiency here is 50%. Receiver efficiency 82%, and cycle, that's steam turbine cycle efficiency here 45%, right? We'll see right now it's 38%. So at the end, if you combine all this efficiency here, this is about between 13 to 17%. The collection efficiency is not good. Collector efficiency from here is only about 50%. You lost a lot of light in the collection. So there you want to minimize the number of reflection. The other problem is your street light, right? If you design high concentration, if it's not parallel, you don't fall into the focal point. Interesting to look at the cost. The cost here, if you look at here, we have 58. That's the collection system. 58 and structure. This one. Does not include the engine. So you have the storage, thermal storage is here, and we have 14% is the power block. I do not know what exactly is that. Okay, and now here is the so this is the parabolic power plant, and again, this is a breakdown, different materials, the cost structure, and so that's the. I thought I was trying to find out. I thought I saw it before. Where is the cycle? Huh? Oh, okay. Yeah. Okay, so that's where it is. Yeah. So the cycle itself is not the.
The bottom one is just the solar field, right? So it's just
yeah. This is yeah. This is so the first one is the overall. The bottom one is the field component breakdown. So the cycle itself is not big part. The collector. Look at I think what's interesting. Look at this here. Metal support structure, 29%. Right. There's a big stuff there. The steel use a lot of steel. And receiver 20%, mirror 19%. Main support is the big one. So if you can cut that cost, that's good.
where's the engine?
The engine is here. 14, that's not big compared to the solar side. Okay. So if you were in Jacob Carney's talk a few weeks ago, he gave he does a lot of the helios stuff. So you have mirrors, tracking the sun, each one, and reflect to the tower, the center there. So it's like a big array of mirrors reflecting the light. So how the solar tower. And what's interesting is this is what I learned from Jacob Carney is that the favorite size, and he put a question mark, but I think the favorite size is actually smaller than 12. The tower you don't want to build too big. Okay, and but the temperature is much higher, so the color efficiency should be higher. And the problem is the focus, and he shows some very interesting pictures. You don't always hit your target. You have a lot of missing light. So if you look at around the focal point, you see a lot of white light that is missed scattered. And so this is the absorber tube, different absorber ways to absorb the radiation. And in this cases, so I showed, I think, in the last lecture, once you get a higher concentration, your absorptivity is more important. The emissivity is less important. Okay, so this, I think those are pretty, it's not really spectral controlled surfaces. They're really not, I think there are only one or two, SPAN probably has, but in US the Kramer junction mostly is a trough, but it does have a tower system. So here it gives you some, in terms of the cost, the field itself is 40%, power is 14%, heat storage 11%, and the engine is 32%. And this is the, here is the structure, reflector, structure 10%, reflector 36%. Drive is drive for the tracking is 30%, and the foundation. So that's the tracking system itself. Okay. The power efficiency, at least from the lumper here, is not much better than the. No, this one is not power. I think. Sorry for that. This one is not power. This is still the 12. I thought I was going to delete this one. Okay. The other form of the generator is a dish. So dish you make smaller. Each one is say 2D, say tracking, and the problem is the generator here. So you have how you can make a small power generator. And here is a Stirling mechanical system. So Stirling engine, and if your mechanical engineer student here, the second year they always build a Stirling engine. It's a burner, benzene-based Stirling engine. So the Stirling engine is very different from an internal combustion engine that's used in the car. You can heat up one side of the Stirling engine, and from external, so external heating, and then you generate the mechanical motion to drive to deliver power. The cost is much higher, I learned. So I do not know anybody is using this. It's not mature. The most mature is the trough. Okay, and so this we have an efficiency number here. Right here is the efficiency. This efficiency is the. I thought I looked at this. I don't. It's a pretty high efficiency. That's but I can't believe this number. It's 29-30%, pretty high. And so this is the Stirling, and that's all I have in terms of the thermomechanical systems. Any questions? If not, I will go back. So this is the big stuff, and I'll go back to it's a simple question.
Are these technologies too immature? You talk about them in terms of watts or latitude.
I think the last two, well, at least Sterling, I don't think it's mature enough to talk about dollar per watt. And some, I don't have exact number. I asked the people around. This is 10 times more expensive than trough. But the heliostat, I have not looked at how many deployment. Let's see, there was one running together with I think the Primer Junction, the trough system. So what I want to do in the rest of the time now is coming back to, we have too many simple handweaving stuff now. Now I want to come back to a little bit more math. And the math, the reason we want to do next is what are you going to say is a selective surface. And it's important to have in the case of concentrating parabolic mirror, it's important to have less reflection. Each reflection, you lose very small amount of energy. So you want a high reflectivity. You want a high transmissivity going through glass. And then once you get onto the surface, you absorb solar radiation. You want to spectrally absorb the solar radiation, but do not re-radiate. So now this is in terms of technology, some of the key technologies. And for those technologies, now you have to come back to the basics, how you can develop further, understand what people have, and develop further. So the basics is Maxwell equation. And I'm not going to spend much time on the Maxwell equation. And if you want to really learn, you should take a course, right? But you all heard about Maxwell equations. It's a set of 4 equations for electric field, for magnetic field edge, and the displacement and the magnetic induction. Right? So I give you the definitions of those symbols: electric field, magnetic field, displacement, and J is the current. And then there are concealed relations related to displacement to electric field, magnetic induction to magnetic field. And those constants are the material properties: electric permittivity, magnetic permeability. Okay. Maxwell equations. And it's a wave equation. It's to describe electromagnetic waves. So if you go to solve those waves, and because that's important, what's important, I say, when you do the particularly selective surface, very often it turns out that you're based on controlling the phase of those waves. Okay, so if you look at a simple solution, a wave has a direction of propagation, wave vector, and it's an electromagnetic field. So electric field, magnetic field, turns out the solution tells you they are perpendicular to each other, and in fact they form a right-hand rule. So you go from electric field to magnetic field, some point to the the propagation direction. And to describe a wave, we have wavelengths and period in time. Period, the inverse is the frequency. Angular frequency is 2 pi times period. 2 pi times frequency. Wave vector has direction, but also has it's the inverse of wavelengths. So wave lambda is 1 over lambda. 2 pi over wave lambda give you the magnitude of the wave vector. And the direction of the wave vector is the unit wave vector here. And then if you solve the equation, turns out at the end that epsilon and mu combined give you the refractive index of the material. This is a property you can look at the different materials. Many times people have measured. It's sometimes it's called the optical constant, but it's not a constant. It's a frequency-dependent quantity. Okay, so you have the real part and imaginary part. And since it's a wave, so the plane wave, simplest solution of this wave is the electric field. It's a function of location time. This is the direction. It's a vector direction of the field, right? And the wave vector, frequency, complex refractive index. So that's your solution for electric field, similarly for magnetic field, and these two E and H perpendicular to each other. And so that's your plane wave solution. This one you can substitute back into Maxwell equation, you find dissatisfied Maxwell equation. Okay. And then, so this is the field. What's the energy? Energy is the product of E and H. And particularly this is time average. This is time dependent. But to do time average, you can simply calculate the E cross H complex conjugated. If you do complex conjugated, you see this I omega t cancel. There's no time there. Okay, so that's your Poynting vector. And if I do that, I will get, for a propagation in a homogeneous medium, the Poynting vector is the real part of the refractive index, mu C0 exponential decay function. So this exponential decay, that's the problem of silicon, we said, right? Silicon photovoltaics, that alpha is a problem. It's too small. Okay, we have to use a very thick one to absorb. And this alpha is the absorption coefficient we mentioned before, and that's related to the imaginary part of the complex refractive index, or extinction coefficient. Okay, so this is the see, plane inside the one medium. Now, what I can control is really with the interface to control. So you got the interfaces. When you have a light comes in, reflection, refraction, right? High school, you will learn that. And because the light can actually have two, you decompose it into two directions. It's a transverse wave, which decomposes two directions. One is your electric field is in the plane of incidence, so direction of coming in norm form the plane of incidence, right? So if your electric field is within the plane, or your electric field is in the other direction. So we have the electric field, if it's in the plane of incidence, the magnetic field is perpendicular, right? It's always perpendicular to electric field, so we'll be in the perpendicular plane. So that's the, in this case, we have transverse magnetic wave, or parallel, if that's for electric field. Different names. I can't remember this. I always just say TM, then I say, transverse magnetic. That's more intuitive. Okay. H field. Okay, that's the, if the magnetic field is in plane of incidence, then electric field is perpendicular, that's TE. And it's perpendicular and S wave. So you have expressions when you look at the calculate the interface, you have to calculate for both solar radiation is a typical combination of 50-50. We calculate it. We say, oh, incident is 50 TE, 50 TM. Okay. Now what happens? First thing is reflection. If you have a smooth surface, right? Angle of incidence equal angle of reflection. So that's a reflection rule. And then refraction is the angle change. Depends based on the refractive index. And then you can actually calculate the magnitude of the field reflected and refracted. And again, I'm giving you the solution. The point is I want to tell you those could be calculated. Okay? And if you want to learn how to calculate, you need to take a course or pick up the book, read it yourself. But it depends on what it depends on is the refractive index of the material on both sides. And so you need to know the property. Very often, although you think people should list it, you go when you need it, you don't find it. That's one. And even people list it, you do solar thermal, you want a high temperature, you don't find it. Okay? So there are a lot of things you can do. Find them. when we do the when we want to design the first surface, oh, let's deposit a film and try to measure properties, right? So those are just the field reflection, and then energy, that's reflectivity, transmissivity. So you do reflection coefficient square, you get reflectivity. Transmissivity, you have to plug in the some factors in the front. But again, those are all depends on the complex refractive index. So the final one is just one example where it's a calculation given the refractive index is between vacuum or air, which is 1, and say dielectric I took a constant, gold I also took a constant, but remember it's not a constant, it's a wavelength dependent. So each wavelength this can change, but here it's calculating only the angle dependence. So if it's dielectric, so kappa is say 0, and here is for the TE wave transverse electric, and here is for the TM transverse magnetic. And then what's interesting is this Brewster angle, and there are certain. So that's how people make the polarized glass coatings. You can choose the polarization. There's a certain angle you can get, let's say, no reflection at the Brewster angle. Gold is a very good reflector if you look at that. Right? Reflectivity is almost close to 1. So when people do selective surface, very often they start with aluminum metal. It's good reflection in the infrared. The problem is it reflects up to about 0.2 micron, or 0.5 micron, or 0.4 micron. But you don't want you do not want to reflect that solar radiation. You want to absorb it. So you try to put materials on the surface to make them absorb between the solar radiation up to 2 micron. And then you still keep the old, say, infrared is very reflecting, which is good, because that means the emissivity is small. So people have developed, like I said, say the different coating, even for the solar thermal, solar hot water, I said they're very cheap, right? $1.5 per tube. You go through the factory, you'll see their vacuum deposition. I saw one vacuum deposition is about 100 meter long, continuously deposited in different layers, and to do it at that low cost. It's amazing. Okay. Okay, so I'll stop here.